Welcome to this session from ARM and Roblox. I'm host Emilio, Senior Software Engineer at ARM, and I'm here with Arseny, Technical Fellow at Roblox, to present our best practices for Vulkan on mobile. I'll start by showing you some of our Vulkan samples, primarily focused around GPU optimizations, and then Arseny will show you how they applied these and other best practices at Roblox, explaining in more detail some of their CPU optimizations. For more than 26 years, ARM technology has powered some of the most iconic gaming devices, enabling the mobile gaming revolution that we see today. Mobile gaming is now the largest and most valuable segment of the global gaming market. In 2019, more than 23 billion ARM Cortex CPUs and over 1 billion ARM Mali GPUs were shipped by our partners. This makes ARM the gaming industry's architecture of choice. At GDC 2019, ARM released a set of Vulkan best practice samples, and these have since then been donated to the Khronos group. Since then, they have been improved with contributions from ARM and also from other GPU vendors. And we also got the addition of some of the popular samples from Sasha Willems. The idea is that the samples should make it very easy to try out different ways of doing the same thing in Vulkan. You can toggle between different paths at runtime while monitoring the impact that they have on performance, thanks to the on-screen hardware counters. Finally, every sample is released alongside an article that explains the theory behind every best practice recommendation, with code snippets, diagrams, and examples where necessary. All of this is now available on GitHub. Let me show you some screenshots. At the top, samples will show you some stats running in real time, such as FPS, vertex, and fragment cycles. And at the bottom, there will be some options to experiment with. This particular scene was also donated by ARM to the Khronos Group GLTF repository, as well as this other scene here. Here are some of the main features to highlight about the framework underlying all of the samples. It is multi-platform, enabling the samples to run on both desktop and mobile. It provides an API that encapsulates some of the objects and makes them easier to handle. It implements shaded reflection to automatically generate some of the necessary objects based on the shaders. And finally, as I mentioned, we integrated a GLTF importer, so you can use our scenes or your own. ARM samples focus on performance, especially around considerations to do with limited power and bandwidth on mobile. Before we dive into the samples, let's go through a quick recap on GPU architectures and render passes. You're probably familiar with the graphics pipeline. For now, let's focus on the vertex and fragment processing stages. This happens in the GPU, which needs to load and write data to main memory. And we here represent those operations with arrows. For immediate mode GPUs found in desktop and console architectures, all the geometry is first processed and added to a queue. Fragment processing then proceeds from this queue one draw call at a time, and for every pixel it will perform depth testing and color shading, reading from and writing to main memory as much as necessary. And these operations, depicted here by the double arrows at the bottom, they require exceptionally high bandwidth and are very energy intensive. If we compare this to a tile-based renderer, in here we move these operations inside the GPU, because what we do is we divide the rendering into two stages. Because we divide the screen into regions of pixels known as tiles, first what we do is we process all the geometry and assign it to these tiles. And then for each tile, we will process the fragment for each pixel using tile local memory. And we will store only the final result at the very end. This can save a lot of bandwidth. The concept of tile local memory is very important, and the Vulkan API will let us optimize our rendering to take advantage of it. Back to the rendering pipeline, let's consider a simple scene like Sponsa. And as you know, all the vertices will be transformed and projected. And after the scene is rasterized, we will be using two attachments, one for color and one for depth, to compute the final image. The collection of attachments and the way they are used is known as a render pass. And in Vulkan, render passes consist of one or more subpasses. When defining a render pass and the attachments, in Vulkan we also need to specify the load and store operations. These specify what to do with the attachments before and after the rendering. So we need to define this for each attachment. Our first samples covers this in more detail. The load operation refers to what to do with the attachment before rendering. The available options are load if we want to load the previous contents, clear if we want to start fresh, and don't care if we can work with whatever is more optimal. For immediate mode renderers, all these might perform similarly, but in mobile or tile-based renderers, load is very expensive. This is because, as we saw, when we are working with tiles, we can save bandwidth if we avoid unnecessarily reading from main memory. In this case, because we don't need the previous contents of the frame buffer, we can use clear or don't care to achieve the same result, and we can save bandwidth. Note that load clear is different from using Vulkan's VK command clear attachments, which will instruct the GPU to explicitly write out a clear value to main memory. And this will be wasteful if afterwards we're going to write out a new value over it anyway. Therefore, please don't use load unless you actually need to, and do not use VK command clear attachments if you can use load clear or don't care instead. Similarly, for store operations, here we're defining what to do with the attachment after the render pass. For color, we might as well store, since we need to present that to the screen. But for the depth attachment, most of the time we will not be needing these values after the render pass is complete. Therefore, you should use store don't care, and this way we avoid writing out the depth values to main memory, and again save bandwidth. If we go back to our tile-based rendering diagram, you can see that we can perform depth testing using tile local memory. And since we don't need to read the previous values for depth, we can use load clear, and we don't need to write out the depth values, so we can use store don't care. This means that the depth attachment will live entirely in tile local memory. And this way, we can avoid having to allocate memory for it at all in the main memory. And Vulkan gives us a way to request this kind of optimization. Apart from defining the right load and store operations, we also need to specify the transient bit in the attachment's usage flags and the lazily allocated bit in the memory allocation flags. This way, a tile-based renderer may avoid allocating memory for this attachment. And we can see all of this in action in the render passes sample. Focus on the external read bytes counter. You can see how the number of reads decreases as we toggle the color load operation from load to clear. Similarly, now in the external write counters, you can see how it decreases considerably as we toggle the depth store operation from store to don't care. Finally, now at the top counters, you can see how we are saving fragment cycles if we deselect VK command clear attachments, in this case a redundant operation. This represents significant savings in bandwidth and therefore power. Let's see it once more time. We can start with load and store, and as we switch to load clear and store don't care, you can see how the graphs show this significant decrease in bandwidth, and therefore we're improving our power consumption. Let's now consider a case where we have more than one subpass. As we saw, we can save bandwidth by making our depth attachment transient. If we have two subpasses, because let's say that we're doing deferred rendering, and we also have one more attachment for the normals, so we have normals, depth, and color, and then in the first subpass we will be computing all these attachments known as the G buffer, and in the second subpass we will be using this G buffer to compute the final lighted scene. Once we're done computing the lighted scene, these attachments are no longer needed, so we don't need to store them in main memory in a similar way as we did with the depth before. All these attachments may also be transient. But this is only possible thanks to an optimization known as subpass fusion. In this case, because both subpasses have a per pixel dependency, a tile-based GPU may take advantage of this subpass merging and process subpasses on a tile-by-tile basis. Doing this allows it to just process all the subpasses for a given tile and store out the very final result to main memory. In our tutorial, we will take you through the necessary setup that you need to achieve this subpass merging if it is available. And the sample shows the bandwidth benefits, again using the external read and write bytes. This time, if you focus on the bottom two graphs, you will see that as we switch between using two separate render passes and using two subpasses, there is a significant change in bandwidth. When we use two subpasses which can be merged, we avoid writing out or reading in the G buffer from main memory, and therefore we are saving a lot of bandwidth. At this point, we need to consider that there is a dependency between the first subpass, which computes the G buffer, and the second subpass, which needs to consume this data in order to compute the lights. This dependency brings us to the complex topic of synchronization. In this case, we will use something known as a Vulkan subpass dependency to make sure that the lighting stage doesn't start until we have completed the G buffer stage. In this presentation, we are going to cover the more general use case of a Vulkan pipeline barrier. Pipeline barriers work with pipeline stages. Here we have a Vulkan enumeration listing all the possible stages of the graphics pipeline. For this session, we are going to consider a subset of these, the ones I highlight here. Roughly, this is how they map to the broader graphics pipeline that we saw earlier. Commands will go through the top of pipe stage first, and then we will find the vertex or the geometry stages, which after rasterization are followed by the fragment stages. Finally, they will go through the bottom of pipe stage. In Vulkan, every command that we submit to a queue goes through some of these stages. The top and bottom of pipe stages are helper stages. Top signals that a command has been parsed, and bottom that the command is being retired. Commands may execute out of order across command buffers and even queue submissions. So in Vulkan, we do not synchronize individual commands. Instead, we use these stages to synchronize the work across them by using the mechanism known as a barrier. With a barrier, we are dividing the command stream in two parts. We are saying that all commands after the barrier must wait at a certain destination stage until all commands before the barrier have gone through a certain source stage. Let's illustrate it with an example. In GPUs like Mali, we find two processing slots so that we can do the vertex and fragment work in parallel. Here, what we're looking at is a timeline, and as the CPU is dispatching the commands, some work will go to the vertex slot and some work will go to the fragment slot. Let's say that we're using color here to represent the work associated to a render pass, and that we are adding one of these pipeline barriers between every render pass. In this case, because the barrier has destination stage top of pipe, the very first stage of the pipeline, this means that all commands after the barrier must wait here and cannot go through the pipeline until all commands before the barrier have reached the bottom of pipe stage, which is the last stage of the pipeline. This means that nothing can execute in parallel, so we're introducing these bubbles between render passes, and this means that the work is serialized and very inefficient. Compare this to this other barrier, which gets rid of the bubbles and maximizes throughput. And we achieve this by specifying both source and destination stages as the fragment stage, because this means that all commands after the barrier may wait at the fragment until all previous work has also gone through the fragment. And this means that work can proceed and do vertex work from one render pass while we're still doing fragment work from a previous render pass. So they may overlap, and therefore we're maximizing throughput. Of course, we're not saying that you should always use this barrier, but you should try and avoid bottom to top dependencies and find the one barrier that best applies to your use case. In this case, since the vertex is not dependent on the previous fragment, this is the minimal correct barrier which covers the use case and hence avoids over-synchronizing. In our sample, we can see this in action once again, and we added high-frequency sampling to the vertex and fragment processing cycles, so that you may see that in the case of a fragment-to-fragment barrier, most of the vertex peaks occur in parallel to the fragment plateau. Now, this is a very simple scene, but in real games we have seen how such a simple change to a barrier has made a significant improvement of up to 56% in FPS. And this takes us to the final sample, which is MSAA or multisample anti-aliasing. As you can see in this detail from one of our scenes, GPU rendering can sometimes result in jagged lines at the model edges. And we can smooth out these artifacts using MSAA. Here you have a side-by-side comparison. How can we explain these artifacts and how does MSAA help? With no MSAA, when we rasterize a polygon into pixels, we only look at the center of the pixel. And we shade it only if the center of the pixel lies within the polygon. This results in this staircase effect, which is what explains the jagged edges. With MSAA, instead of considering only the center of the pixel, we're looking at multiple samples. Let's say in this case we're looking at the location of 4 samples, and we will shade the pixel if any of these 4 samples lies within the polygon. So now we are considering a couple more pixels around the edges. We still run the fragment shader only once, and we are using the coordinates of the center of the pixel, but then we save the result of the fragment shader to all those samples that lie within the polygon. Then we average the value of all the samples, and for instance, if 2 out of the 4 samples lie within the polygon, we will be using 50% of the color of the fragment shader. And this results in a much smoother gradient between the fragment color inside the polygon and the background. The step where we average the samples is known as the color resolve operation. And this resolve operation in tile-based renderers may be carried out using only tile local memory, and therefore we can save a lot of bandwidth because we don't need to write out all the samples to main memory. We can do our rendering using 4 samples, but then we average all the colors and we write out only the final color. And as we saw earlier with the G-buffer and the depth attachments, this means that the multisample attachments may also be transient. To do this in Vulkan, as you remember, we need to specify the right load and store operations, as well as the memory flags for the attachment. And another thing we need to do in this case is to specify the resolve attachment. This is the destination of the color resolve operation. Now, we need to do this at render pass creation time. If instead we use VK command resolve image later, we will be incurring into a very high bandwidth penalty. Here's why. If we specify the resolve attachment up front, what happens is that we do 4x or multisample anti-aliasing on tile, and then we just write out the average or the resolved color to main memory. However, if you use VK command resolve image, what happens is that the GPU needs to save all the samples to main memory to then read them back and carry out this separate resolve operation pass. And this is very expensive and wasteful, and you can avoid it by specifying the resolve attachment up front. And our sample compares these 2 ways of resolving. As you see, as we enable for MSAA, there is very little impact on the bandwidth, but as soon as we toggle to using VK command resolve image, you can see there is a very big increase in bandwidth. I'll toggle another time, and you can see the delta there in the graph. Now our sample goes a bit beyond this and also shows you how to resolve not only color but also depth, which is very similar, but it uses a new feature introduced in Vulkan 1.2 and requires a bit more to set it up. And now Arseny will tell you about optimizing Roblox.
Thank you, Emilio. Now let's talk about optimizing the Roblox render, and I'm going to specifically focus on the CPU optimizations because the GPU part has been covered earlier. So what is Roblox? Roblox is an online multiplayer game creation platform. The word platform is key here. We don't build the content of the games for the platform, our community does. We run on a lot of different software and hardware platforms. We use a lot of different graphics APIs, but of course the focus today is on specifically Vulkan on Android. So because we don't build the content, we aren't really in control of how complex that content is. And the main avenue for us to make sure this content performs better is to optimize the engine to make it run faster. Historically, the games, the showcases, the levels that our community builds tend to be geometry and rock heavy. Here's a few examples from various games and showcases, and if you look at the bottom left screenshot, the trees in the middle, these are actually not meshes, they're built out of individual small tiny primitives. It's because of this, the cheaper the draw calls for us are, generally speaking, the faster the frames render. Of course, this is assuming that the games are CPU bound, which they don't always are, etc. But the cost of the draw call is important to us. Now, we don't have a whole separate Vulkan renderer. We have a common rendering interface abstraction, and then we have an implementation of this for every single graphics API, Vulkan included. And so really our goal is to make sure that the implementation of this interface is really efficient for Vulkan, but of course, we also want to make sure that this interface itself is easy to use by our rendering engineers. So there's a bit of trade-off here in terms of ease of use versus performance. And we care about the performance in a single thread of execution, but also we want to make sure that you can use the interface to record the commands to render the frame from multiple threads. So contention and things like that are important as well. Now, this is an example of how our interface looks. And you can see it's pretty simple, it's pretty straightforward. So you create a command buffer, you begin the pass, and you bind the program, which is the collection of shaders. Potentially you set some other render state that's necessary. Then you bind the resources, the buffers, the textures, and then you submit the draw codes. And so we're going to talk about every part of this process and how it maps to Vulkan and how we optimized it to be more efficient on the CPU side. So let's start with command buffer management. And so for a lot of these, there are ARM samples that discuss trade-offs around the implementation and highlight several possibilities and benchmark them. So whenever there is a link in the top right corner to an ARM sample, check that out. So it seems very simple to allocate and use command buffers in Vulkan. You can just call vkallocate to allocate it, and then once you're done recording, you call qsubmit. To q is for execution. However, it gets really complicated in presence of multiple threads, and also even on a single thread, it's more nuanced than that. So you can't record command buffers that are allocated from the same pool concurrently. So you need several pools for different threads. And also once you submit the command buffers for execution, you can't reuse that command pool up until all of these command buffers are done executing on the GPU. And also all of the calls involved are not free or particularly cheap. For example, vkallocate has visible overhead on some driver implementations. And also vk free command buffer doesn't actually free the command memory on some driver implementations, so you can't just use allocate and free and expect your memory to be constant. So because of this, instead of just using a command pool or two, we use a pool of command pools. And so whenever you create a command buffer, you need to get a pool that's not used from the current active set. So then you can record the data for this command buffer. And then once you commit the command buffer, we don't actually submit it for execution on device yet. We just record the fact that you want to execute it. And then other threads can start reusing that command pool again. When the frame ends, all of the command buffers that have been allocated and all of the command pools that have been allocated, they can't be used again. So the command buffers are submitted for execution with one call to vkqsubmit, which is optimal from the point of view of the overhead of the submission. It's not always optimal from the CPU-GPU latency, but it works out for us. And so then once that frame is done rendering on the GPU, which happens a few frames later, you can recycle the command pools and command buffers involved. We call the reset command pool command to free the memory and get the command buffers ready for execution again. It's important to note that you don't actually need to free individual command buffers with that technique. So once you reset the command pool, you can start recording using command buffers that you have allocated previously. So this gives us a really good balance in terms of the performance overhead and ease of use, and also this is pretty efficient memory-wise. Now, once you have a command buffer, you need to begin a render pass, and render passes are quite complicated. There's a lot of pieces of state that you need to manage. And the biggest challenge for us, at least, is that there's just no global view of the frame. So when you have a render pass that renders something to the texture, you don't know how this texture will be used in the future. And because of this, you can't always do an optimal barrier setup and things like that. So we don't solve this using render graphs like some other renderers do. Instead, we have the balance between the information that is specified by the rendering engineer and the information that's inferred. So we do specify what textures you need to render to, of course, in each pass, but also the load store actions. So do you need to load this texture from memory? Do you need to store it? Do you need to clear it? But we actually don't really specify anything else, and everything else is inferred from just this setup. So also unlike Vulkan, we don't pre-create the render pass objects. We don't force the rendering engineers to do that. We lazily create and cache these objects inside the rendering implementation, which seems suboptimal, and it does cause the first frame of our render to potentially be slightly longer. But because the frame structure is highly regular, all subsequent frames are going to be fine. So this is not a really big problem. So to do image layout transitions on the render pass boundary, and I should mention we don't do resource transition within the render pass, and also advise not to do that. So you have to know what state the resource is going to be used in the pass, and also what state it was before the pass and what state it should be after. And so in some engines, the way they solve this is they keep the current resource state for every resource. However, this doesn't really work well with multi-threaded recording. And so because of that, instead of the current resource state, we have a notion of the default resource state. So for every resource, we know what we should expect the state to be between the render passes. For example, for textures that can be read in the shader, this is shader read only. And then when you begin the pass, you need to transition from that state to the state that should be used inside the pass, and then at the end of the pass, you have transition out. This seems suboptimal, and it would be if done naively. However, we use the load store actions to help us infer a bit more information and to replace some of these transitions with cheaper ones. So for example, when you render to a pass that needs to render to a texture that has a load action of don't care, so you don't load this texture from memory, you could transition from shader read only or whatever state it should be in to color attachment optimal, but you can also transition from undefined. And on some drivers and some GPUs, this actually saves an appreciable amount of time on the GPU side, because the driver is free to assume it doesn't need to preserve the contents of this texture. And so we do the same for load and store. So when you don't store to a texture, instead of transitioning from color to shader, we can transition from color to undefined. And for pipeline barriers, we do something similar where if you don't store the texture, we don't need to synchronize it. But also we make a simplified assumption, which is that if you do store the texture, it's only going to be used in the fragment shader stage. And if this texture is used in any other stage, you need to specify that explicitly. So this means a bit of an extra work for the rendering engineers when, for example, you need to have a render pass and the contents of the resulting textures used in compute stage. However, it's really, really important for tilers to default to kind of fragment shader stage synchronization, because this makes sure that the vertex and fragment stages can run in parallel by default. So now for pipeline states, we don't really do anything special here. So we lazily create and cache the pipeline objects. There is an in-memory cache for these, and then there is an on-disk cache that gets loaded when the game starts into a VK pipeline cache object, which means that on subsequent runs of the game, the driver doesn't need to recompile the shaders redundantly. Now, This does mean that when you bind the unique combination of shaders and states for the first time, there's extra work that needs to be done. However, for us, the number of shader permutations and state permutations isn't very high. It's in the low hundreds. And so because of this, and because of the regular frame structure, generally speaking, most of the cache is filled very quickly in the first few frames, and then it's serialized to disk, so subsequent runs are also fast. However, for the use of this cache for multiple threads, reducing contention is important. So for steady state performance, we try to make sure that whenever we need to look up entries in that cache, we don't need to log any mutexes to do that. For that to work, we have the cache that's implemented as 2 hash tables instead of 1 hash table. So the first hash table is only ever read from during the frame, and so this means you can read from it concurrently from an arbitrary number of threads without any mutexes. And if we don't find the entry in that cache, we need to consult the second hash table, which has to be protected by a mutex. It could lead to creating extra pipeline states. It could be expensive. However, once we have created the object, at the end of the frame, we move all of the entries from this read-write hash table to the read-only hash table. So this means that at the end of the frame, all of the entries migrate to the read-only map, and in the next frame, the access is contention-free again. So this is a really useful technique to reduce contention when you use many threads to record commands. Now, once we have the pipeline state, we need to bind the resources to the pipeline, and our descriptor management scheme is slot-based, so we only have 2 namespaces. We have namespace for buffers and textures, and for each one we can just say, oh, I want to bind the buffer to the slot 5. This is a blend or a hybrid between a Meta-like API and OpenGL-like API, maybe the 3D11-like API, so it has a bit of a differences with all of these. Like, for example, instead of having per pipeline stage slots, we actually have just a single global slot namespace for buffers. So the buffer with index 1 is index 1 and vertex and fragmented compute and any other stage, which actually tends to be quite convenient from the programming perspective, and also this maps pretty well to Vulkan specifically. Now, when we create the pipeline state object, we, generally speaking, already know which resource slots are needed because we can query the shade reflection metadata that says, oh, we need a constant buffer in slot 1 for the vertex shader to be. So we can configure the descriptor set layouts without any further user input. And now when you bind the buffer texture objects, we just record this information, and then before we do the draw call, we need to actually allocate and update the descriptor sets. To allocate a descriptor set, you need to allocate it out of the pool, and so the question is, how do you configure this pool? And this can be challenging, especially if you take multi-threaded recording into account and certain other issues. For example, it's tempting to just have a pool, a descriptor set pool for every unique shader pipeline configuration. So you know this shader pipeline uses 3 texture descriptors and 2 buffer descriptors, so allocate for that. However, this tends to be inefficient memory-wise because there could be pipeline objects that are used very rarely in the frame, and generally speaking, you would over-allocate sets for these descriptors and waste memory. And also, it's hard to manage multi-threading with this approach because for multi-threading to be efficient, you really can only allocate and update a specific descriptor out of a specific pool on a single thread. And so it's hard to manage this when every single shader pipeline object could come with its own pool or pools of descriptor sets. So instead, we just have a single type of descriptor pool in the entire frame, but to make sure that we are memory efficient, instead of configuring it for the worst case, we configure it for the average case. So we know that in general, in our frame, measured across many different types of games and rendering techniques and things like that, we tend to use like 1.5 buffers slots per descriptor set and like 3.5 texture slot. And so this is what we allocate. Now, it doesn't mean we can't allocate a more complex descriptor set out of this pool. It just means that if you have a frame that's mostly using simpler or more complex or imbalanced descriptor sets, you may waste memory. But if your averages are computed carefully, then it, generally speaking, isn't a problem. And this makes it really, really simple to make sure that the update of the descriptor sets is thread safe. because this just means that for a single thread of execution, we can keep the current descriptor sets that we are currently allocating out of, or current descriptor pool that we are allocating sets out of. And if we run out of space in the descriptor set pool, then we need a new pool. So it's the same pool of pools concepts that we used in the command buffer recording. And then at the end of the frame, we can, or when the frame is done rendering, I should say, on the GPU, we can recycle the spools again similarly to the command buffers. Instead of freeing the descriptor sets, which you really shouldn't do, we just reset the entire pool. And these sets have to be updated after you allocate them. We just use vkupdate descriptor sets for this. We use descriptor templates from Vulkan 1.1 when available. This saves us a bit of the CPU time on some drivers. And also notably, we don't copy the descriptors out of existing sets. We just allocate and update the set in one go, which tends to be a bit more efficient on some drivers. Now, for textures, you really need to allocate and update the descriptor sets, but for buffers, you don't have to. And this is actually really important. So instead of managing each individual uniform buffer as its own object, we tend to use large buffers that we suballocate from. And instead of updating the buffer descriptor inside the descriptor set, which requires a new descriptor set, you can just update the offset, which requires rebinding the descriptor set with a new dynamic offset. So this dynamic offsets feature is really important for us to reduce the CPU overhead of updating the uniform data. And also it saves us memory because we don't need as many buffer descriptors during our frame. And in general, I would say what you'll find is that the Vulkan driver for any vendor is much faster, much more efficient than a GLS driver, which is good, but also this means that it highlights inefficiencies in your code that could have been hidden previously. For example, we had to do some work to reduce the cache misses in our own rendering abstraction. On GLS driver, it didn't really matter because the GLS driver overhead was just so high that it was lost in the noise. But with Vulkan driver being more efficient, the efficiency of our code is more important. So it's a good forcing function. And also there's a few just nice general Vulkan optimizations that you could apply. The general rule of thumb is if you cannot call a Vulkan function, it's probably faster to not call a Vulkan function. For example, we do some filtering on the pipeline setup and things like that in our code, because in our code is just a comparison which is basically free. And also for some Vulkan functions, you could see some overhead in going through the loader layer. And so if you use the specialized loaders such as Vulk, they can load the function pointers using vk get device proc address. And these function pointers, calling these function pointers goes directly into the driver in most cases, which for us gains a couple of percentage points on some implementations in terms of the throughput. So what do we get out of all of this work? The results that we see are really good. So the results that we see are, generally speaking, 2 to 3x faster CPU side render time, but this is not measured in terms of how much time it costs to record a single draw call. This is measured on the entire render frame, including portions of this render frame that are actually not API specific. So it's a real world test. How much time does it take you to submit commands for this render frame from the start of the frame? And these gains we generally speaking see on all vendors. You can see a frame here which takes like 13 milliseconds to record on an ARM GPU, on an ARM driver, and the same device with GLAS with our renderer takes 3 times as long. And this is all in a single thread of execution, so we haven't deployed the multi-threaded support for the command recording in production. So I'm hesitant to draw conclusions from the performance numbers that we may have seen internally, but it seems to scale pretty well. Of course, there are caveats around things like big little cores, so you can't really scale your render command recording across, for example, 8 threads on an octa-core device and expect 8 times better performance. And so with that, I'm going to hand it over to Emilio to finish this talk and to talk a bit about further reading materials.
Thank you, Arseny. Here we have some references that we think are very useful to go into more detail and understanding what we covered today. I wanted to highlight Arseny's article on writing an efficient Vulkan renderer because it was very useful as the basis of some of the samples in our repository. Speaking of which, these are all the samples that are there today. And I'll encourage you to please contribute either by giving us feedback, ideas on which samples to work on, or even developing your own samples. We accept contributions and we'll review them for you and help you find the most optimal best practice for Vulkan. I'm hoping this session was useful, and again, thank you very much for joining.